Hi, my name's Dan Mathews. I'm a senior lecturer in the School of Mathematics here at Monash, and in this talk I'm going to tell you a bit about a field of mathematics called topology, which I think is a lot of fun. It's an area of mathematics in which I do research, and it's one I really like. So I'm very happy to be able to tell you about it today. But before I get into topology, I think that I might just say a little bit about mathematics in general and what mathematicians do and how we use mathematics, what it's about. Okay, so let's just begin by asking a general question. Who does mathematics? Well, people everywhere do mathematics, all areas, not just in universities where I do it, but also in industry, government, all sorts of institutions, and also just everyday people. It's used all across many endeavors. So things from bioinformatics, biology, biostatistics, climate science, all the way across all sorts of sciences, all sorts of engineering, all sorts of industries, and well, just endeavors in life and in the world. So things from data science to economics to finance, health, logistics, teaching, all over the place. So the first thing I want to say is that if you're interested in studying mathematics, it's a really great idea. I think not only because I think it's a great subject, but also because it's used so widely. And it's, if you're interested in your employment prospects, it's definitely a good thing to do. There's also pure mathematics, of course, which is, well, the research that I do in mathematics tends to be quite pure mathematical, and well, topology tends to be a fairly pure mathematical topic, although it does have many applications. Yeah, so let me just say a little bit about what mathematics is about, at least from my perspective, because I think that in school, the impression that you tend to get of what mathematics is about is not always the same as what people who do mathematics for a living think that it's about. Well, for one thing, it's often very applied to the real world, and there are many models that describe all sorts of aspects of the world in all the fields I just mentioned. And it can often be a good way for thinking about all sorts of systems and processes in science, engineering, society, and all over the place. It's also often done for its own sake, for pure mathematics. This is primarily more in universities and research institutions, but it's a fruitful thing to do. And the good thing about pure mathematics is that you don't know what the consequences are going to be. There are tons of examples of pure mathematics being done for its own sake that sometime down the line, sometimes centuries later, leads to all sorts of interesting applications. So it's certainly a worthy endeavor. A lot of people coming who don't have much of a mathematical background often think that people like me, mathematicians, people who use mathematics for a living, must just be really good at doing big arithmetic, lots of equations, big numbers, and really good at doing those exercises they remember from their high school textbooks. Well, that's not what I do, at least, and it's not what most of my colleagues do. So that's not what I think it's about. I think it's about things like this, things like truth. You know, there's no, in some sense, there's no more certain truth than what you find in mathematics. The fact that 2 + 2 = 4 is true in a way that a lot of other things in the world are not true, even other scientific truths, even, sort of physics and chemistry, where things come about by experiment, they're only as certain as the next experiment. And in mathematics, there's a bit different. The level of certainty is somewhat higher in a certain sense, although we do often also think very critically about questioning our assumptions and questioning our axioms and things like that. So it's about truth. It's about finding deep underlying reasons, abstract reasons that underlie all sorts of phenomena in mathematics, and then in turn in other sciences. It's about doing logic, making precise deductions, but also often in a quite creative way. So especially in pure mathematics research, the way that you apply mathematical ideas is often done in a highly creative and even intuitive way. So it's certainly not a machine-like endeavor, at least for most mathematicians, although many of them do use computers and work on algorithms and things like that. It's often very elegant. It's often an aesthetic affair. Often mathematicians will sort of try to find the nicest proof, the most elegant, shortest, most concise, really crystallizing the reasons for why things are true. It's about proof. This is mathematical proof is a concept that is very different from levels of proof in other types of other fields. And it's all about understanding the world, the mathematical world, the physical world, and everything in it. Okay, so enough generalities. Let me tell you a little bit about topology. So this is, as I say, this is a field of mathematics in which I do some research and teaching, and I just think it's a lot of fun. All right, so it's an area of mathematics. It's very big, just as there's, algebra, there's geometry, there's number theory. Well, there's also topology. You rarely see it at school, except for one or two bits that might make it into, your secondary school classes, but it's really not in the curriculum. Okay, so without giving you a sort of, a semester-long lecture course, which I highly recommend you do when you get here, I can just try to give you a vague definition of the sort of thing that topology is. So topology is like a type of geometry where we just actually forget about geometric concepts like lengths and angles, and all we're interested in is the shape of objects. So let me give you an example here. So as you can see there, we've got a cube, but the cube in topology is equivalent to a sphere because you can sort of morph it. Imagine it's made of plasticine or rubber or something, and you could morph it into a sphere without sort of putting any holes in it, without ripping it, sort of by a continuous or smooth deformation. You can turn that cube into a sphere, and likewise you can go back by sharpening some edges. So topology is the sort of study of these sort of shapes where you sort of don't care, like, you think of a cube and a sphere as the same thing. Similarly, in topology, a heart is equivalent to a disk. So what we've got written there is I heart topology. I love topology. And one that you often see in a description of topology is that a topologist can't tell the difference between a coffee cup and a donut. So let me just have a bit of donut here. And why is that? Well, let me show you a bit of an animation which kind of illustrates why we would think of a coffee cup and a donut as the same thing. So here you can see we've got a donut, and now it's going to morph sort of continuously as if it were made of plasticine or rubber, and there it is, turned into a coffee cup. And we didn't stretch it, we didn't rip it, we're just sort of going back and forth by smoothly or continuously deforming it. So the coffee cup's the same as a donut. They're different though from things like a cube or a sphere, because the donut or the coffee cup has a hole in it. You can see the hole in the donut, and as you can see in the coffee cup, the hole becomes the handle, all right, or donut. Okay, so this is the sort of way we think in topology, and it's kind of fun, I think. Okay, so sometimes it's described as rubber sheet geometry, and it really does give you new ways of thinking about geometry, about space, about all sorts of things. It comes up in art too. So there's a wonderful, all sorts of art that has topological ideas in it. M.C. Escher, the Dutch 20th century artist, has a bunch of works that are really interestingly mathematical and topological. And this is one of his. It's ants crawling around on a little surface here. I've even got a little animation of it. And okay, so that sort of surface is sort of made into a lattice or grid, but you can sort of see that it's like a ribbon, perhaps. And you can see the ants coming along here, coming along the front, going over the back and around. And when they come back to the same spot on the ribbon, they're actually on the other side. So one side of the ribbon or the surface becomes the other side. This is something called a Mobius strip, which you might have seen before. It's an example of a topological phenomenon, which we call a non-orientability. So it's an interesting sort of thing, which is very much part of the subject of topology. Great. So that sort of thing, that's one sort of example in art. Here's another example, which comes from video games. And by video games, I mean even ones that I know, very, very old school ones that even, I played back in my day. The concept of wraparound. So that goes back all the way to games like Pacman. So I'm talking, early 1980s here. Fun stuff. And so I think, though, it's such a famous game, people still tend to know about it. So, in the game of Pacman, you play your sort of Pacman, and you're going around and trying to eat everything before the ghosts get you. And off you go, and you can go around and eat and so on. But one thing you notice is that you go off the side, go off the left-hand side, you come back in on the right-hand side. And when you do that, you've sort of wrapped around with a phenomenon called wraparound. It comes up in Pacman. Now, you might see that I've got two games there. Pacman. Yeah, but there's also a version with a female protagonist. Weirdly, they didn't call it Pac-Woman. They called it Ms. Pacman for some reason. I don't know. I don't make these things up, and that's not what I would call it. But there's also another version of the game which has even better wraparound. So why don't we play that? Here's Ms. Pacman. And here's Ms. Pacman going around on video game, and you see there's a couple of portals off from the left, from the right to the left, and vice versa there. So you've got this idea of wraparound. And it comes up in video games, and it's actually an interesting thing from the point of view of topology. So let's see how it relates to topology. What's the topology of Pacman? What does that even mean? So here's what I mean. Let's consider a sort of mathematical idealized version of Pacman where there's not just sort of one or two sort of tunnels off from the left to the right, but sort of in a more ideal version where you can exit the screen at any point and enter on the opposite side. So what I mean is something like this. You have a Pacman here moving up, up, and when Pacman goes off the top of the screen, it comes back in on the bottom. Okay, so anywhere on the top, it comes back in on the bottom, and similarly, anywhere that Pacman goes off to the right, he comes back in on the left. So just like here, going off to the right, coming back in on the left. Okay, so when you do that, let's think about what that means. And it leads to some interesting topological ideas. So one way you can describe it is in this picture here. We've got a square, so that's supposed to be the screen, but when you go off the right-hand side, you come back in on the left-hand side. So it's effectively as if the right side and the left side are glued together or wrapped around. Well, we can sort of imagine taking that square and sort of gluing it up. Similarly, the top is identified with the bottom. When you go off the top, come back in the bottom, you wrap around that way as well. So topologically, the way we think about it is we take that square and we wrap up the two sides, right, left, and then we wrap up top and bottom as well. Okay, opposite sides identified, glue them together. And what does that look like? It looks like this. So you start from that square, glue up top and bottom. Well, that makes a cylinder. That's something you can do with a piece of paper at home. And then the left and right have become the two circles at the ends of the cylinder, and you want to glue them together as well. And when you do that, what you can see it's harder to do with a piece of paper is that you get the surface of a donut, which technically we call a torus, just because we don't want to sound like reading donuts all day. So Pacman and Ms. Pacman live on a donut. Okay, yeah, let's think about this a bit more because it's kind of fun, and we might even play a game about this. What does life on a donut look like? What's life like for Pacman? Well, thinking about this, so Pacman looks off to the right, but when Pacman looks off the right-hand side of the screen, what does he see? Well, he sees off to the right-hand side, which comes back in on the left-hand side, and he sees a copy of his backside, copy of himself, sees his own backside. So, all right, so that's an interesting idea, and this is actually one that we can play with and make all sort of fun games with, and I'll share with you a couple now. So there's a bunch of torus games online at this website, which I've got the URL here, geometrygames.org, and yeah, let's play some just to get a feel for the sort of things that happen in topology. So here's one. It's a maze. We have a mouse here, and the mouse needs to go around the maze and get to the cheese. And okay, so we'll go around. Obviously, we get stuck if we just try to stay in the square. But if we go off the side, well, it's a torus, so we come back in on the other side. And so perhaps you can sort of see, if you think about it, how to get to where you need to go here. And this is quite a tricky one. There we go. I think this game generates them at random. Okay, so there you go. Now let's think about what life is like for that mouse. As far as that mouse is concerned, like the maze is not the box we see. The maze is instead, like if you look off the side, you see back around, as I was just saying, Pacman. So let me just shrink this a bit, and then note that what the mouse would actually see is something more like this. You sort of see it repeating. Now, every copy of this mouse is the same mouse, but when you look around, you see a copy of yourself, and so you see something like this. And so doing this maze is often expressed in this way, and this is the way that topologists often think about this sort of phenomena. Okay, and so we can then go and try to get our cheese, and off we go, and there we go around, and we got our cheese. Very good. Okay, and yeah, so there's lots of other games here. On this, so this is made by mathematician Jeff Weeks, and in addition to the maze game, there are many others here. We can play tic-tac-toe in a torus. So there I am placing an X, computer's placing an O. And yeah, so it's sort of repeating. And now here I am winning because I got 3 in a row on the torus. Okay, so yeah, you can have lots of fun playing games on interesting topological surfaces like this one. And why stop in 2 dimensions? So you can go to 3 dimensions as well. And yeah, I think there's 3D tic-tac-toe here as well, where this one's a bit harder to see. Okay, so I'll shrink down to a cube, just a cube, whereas we had a square before. And now you can imagine sort of doing, placing your noughts and crosses or red and blue squares, cubes and spheres like this, and seeing what happens. So there we go. And you can sort of see, there we go, I've won again. So you get an interesting wrapping around now happening in 3 dimensions. So all these interesting things happen in topology. And yeah, you can play those games yourself in your own time, and you can study the stuff here at university. Yeah, so what we just saw was a 3D version of Pacman there, but we had a cube. And when you go off to the right, come back in on the left. When you go at the top, come back in on the bottom. You go at the front, and you come back in on the back. So that's what we call a 3-dimensional torus or 3D donut. And it's a 3-dimensional space. And you can think about what it's like to live in such a space. Well, just sort of had a picture of one. More generally, you know, if you're not thinking about tic-tac-toe, what you'll see is sort of a cube which is repeating and somehow tessellating 3-dimensional space. And the study of 3-dimensional spaces like this, or 3 manifolds as they're known for those of us in the know, is a very active area of research. It turns out that there's a lot still unknown about them, and there's been some really big breakthroughs in the last 10, 20 years. Yeah, we have a lot of interesting software which we use to investigate them, one of which is a flight simulator. So why don't I show you this one as well? Some fun topological software. It's called Curved Spaces. And so the first one I'll show you is a flight simulator for a space like this one, the 3-dimensional donut, 3-dimensional torus. So here we go. So the idea here, we're in a universe, which is a 3-dimensional donut, 3-dimensional torus. And so this universe just basically consists of the Earth and us. And but because it's got this sort of wraparound property, we see many copies of the Earth. So this is a universe with an interesting topology, as we would say. And we can sort of fly around here. We can sort of steer around and even put a bit of a grid in, so you can sort of get a feel for these cubes. Okay, so yeah, so these are the sort of some of the sort of objects that I study in my research with some colleagues here, and there are many more complicated ones than that. So that was a cube with its sort of faces being identified by a wraparound. But why stop at cubes? You know, there are more complicated 3-dimensional objects, and they all lead to interesting things. So here we've got a picture of a dodecahedron. So as you may or may not know, dodecahedrons are sort of what we call a regular polyhedron. It's a sort of 3-dimensional shape with 12 faces. They're all pentagons. And I'm going to show you one where, just like on the cube, we sort of identify the opposite faces. So just kind of is illustrated here. This top pentagon is glued up to that bottom pentagon and all the others. And that now becomes really hard to visualize. But I'll show you what you get. This space which we're now flying around in. But now instead of the frames making out cubes, which are tessellating space, they're actually dodecahedra. And now if you think about dodecahedra in space, if you've ever seen a model, the angles in a dodecahedron between the faces are about 117 degrees. So they don't actually tessellate very nicely. And what happens then is that you have to think about curved geometry, curved space, in order to be able to tessellate these things. But it turns out you can, and it leads to all sorts of interesting stuff like this. So this is an example of a space with what we call spherical geometry. So this is the sort of objects that I study in some of my research, so-called 3 manifolds. So that one's called Poincaré dodecahedral space, named after Henri Poincaré, that's a mathematician there. And there's a sort of more detailed picture of this tessellation by dodecahedra in a curved space. Yeah, and this is sort of this is not just pure mathematics here. It also has very important applications. So our universe, as we know, has 3 dimensions of space, or at least looks like it. And so there's an interesting sort of question here, like our universe, does it do anything like this? What is the shape of our universe? Does our universe repeat like this? So that's a quick question for astrophysicists or cosmologists, but there's also a mathematical question here. So this pure mathematics question, or which is really a topology question, what are the possible shapes of the universe? What are the possible answers for that astrophysics or cosmology question? And so understanding 3-dimensional manifold bears on these huge questions. And so it's one of the reasons why 3-dimensional spaces are such a huge field of study in topology. So here I've got a picture which you may have seen. It's a picture of the cosmic microwave background radiation. And so some scientists have looked at this data and asked, well, if you were living in a three-dimensional torus, donut, or this sort of dodecahedral space, which I was showing you, well, you should be able to see copies of yourself. And they look for patterns in the data to see if we do see sort of repeats like that. So if you can see repeats in here, then you would see that we live in a sort of universe with this sort of crazy topology. So some studies have looked at and suggested that possibly it's like a dodecahedral space like the one I just showed you, but the evidence is pretty weak. I would say it's very weak myself. You can sort of see this was the best fit they could find. These 12 circles here are supposed to be the sort of 12 copies of the Earth, or the same thing. And those 12 circles do not look very similar, if you ask me. So nonetheless, it's an interesting question, but the evidence is probably not. Okay, so that's a little brief introduction to topology and some of its ideas and some of the fun you can have with it. So if you're interested in learning more about this stuff, or mathematics more generally, what do I recommend you should do? What are my suggestions? Well, of course, you should study maths at school. You need all that stuff to understand topology properly. And although, the things I've been showing you are things that, you don't need a really strong mathematical background to see what they are. To actually do research with this stuff, you need to study a lot. And that's why we have a course in topology here, which follows on from the introductory courses. So study maths at school. And that means at VCE level doing maths methods. And I would also say, if you can, do specialist maths. Because if you want to study maths at uni, you basically got to do that stuff anyway. And if you don't do it in specialist maths at year 12 level, then you're going to have to do it in first year. And so it'll take longer to get to the other stuff. As to how it goes, if and when you get to university here at Monash and you study mathematics, there are first year courses which cover general mathematics. So as I say, filling in things from secondary school, like the content of specialist maths, and then going on to more advanced stuff. And then in second and third year of undergraduate studies, you can get into more specialized topics. And we do have one in topology. As far as topology goes, Monash has a really leading group of researchers and lecturers in geometry and topology. I'm very happy to be one of them, and I find it a really fun place a great place to do that research. But above all, I'm not saying you have to study this stuff, of course. You should study what interests you, and you should be curious and open-minded and think critically. And enjoy what you're doing. Great, so thank you for listening to this. Hope you enjoyed topology and enjoyed what I had to say. And there's my email address if you'd like to contact me or ask me questions. Thank you very much.